Hello everyone, we're going to cover chapter 8 from the Prince book, so all about regression. We'll start with linear regression and work our way up through Gaussian processes, sparse regression, all the way up to relevance vector regression. An example of regression would be where we take an image encoded as a 100-dimensional vector and then try to estimate the continuous domain pose of each of the joint angles. Maybe 55, maybe more, but for our purposes today we'll probably talk about just regressing one continuous value at a time. We'll approach this initially from the discriminative approach, so modeling the probability of w given x, the continuous variable given some observation vector x. Initially assuming that each world dimension is predicted separately, we're going to model w given x and theta, so our regressed value w given our observations x and model parameters theta, using a normal distribution on w. And here you should see that the mean is some linear function based on x and a constant variance sigma squared. For a fixed value of x, we'll have a probability of w that varies as a function of w, so nice normal distribution centered at some value, and that value changes as a function of x, as you see in the graph on the right. Now, without changing our model at all, we're going to tidy up our notation a little bit. We're still going to have a linear relationship between x and the mean of our normal distribution, but instead of having this constant out in front and a phi vector times x, we'll make this vector a little bit bigger so that it can include the phi 0. To do that, we'll prepend a 1 in front of the rest of the x vector, and that'll be our new x vector, a slight abuse of notation. And we'll prepend the phi 0 at the beginning of the old phi, so our new phi is just one element longer. Notice when you multiply phi transpose x using the new definitions, you'll get the same old linear relationship between x and our mean of our normal distribution. Another notation trick we can introduce is to talk about all our data, labels and sensor data, in larger vectors or matrices. So far we've been talking about each input datum xi and its corresponding label wi. But we can combine the wi's into one long vector w, bold w, and talk about the probability of that bold w given a matrix of all of our measurements and our model parameters theta, and it'll still be a normal distribution on bold w as a mean that varies as a function of x, just like we did previously, and it has a spherical covariance sigma squared times this big identity matrix. If we look at the dimensions of these new elements, we'll see that x has d rows and it has I columns, and we'll see that w has I elements in it, so it's going to be I by 1. When you take x transpose, that'll be I by d multiplied by phi, which is d by 1, you'll end up with a result that is dimension I by 1, which makes sense. That means we have a mean for every element of the w vector. Now, we can learn model parameters for theta in 3 different ways: maximum likelihood, maximum a posteriori, or the Bayesian approach. For now, we'll just start with the maximum likelihood version. So we just care about maximizing the probability of w given all of our measurement data and our model parameters. We can do the same process as we did before, where we look at the log likelihood, take the derivative with respect to our model parameters, and solve for our maximum likelihood phi and our maximum likelihood parameter for variance. You have all of these elements already. You have your data, you have your labels w, and this I here is the number of elements in w. All right, so this result shouldn't look too surprising. Now we can plot our model probability of W given X, and our normal distribution looks like a nice linear regression where for various input values of X, we have different predicted values of W with some uncertainty around each of them. Notice that our model goes through the blue training data points, but it's not perfect. It doesn't go through all of the points, so it misses some of them. Because it's just a linear regression, it doesn't have the flexibility to go through all of them. And also, it doesn't seem to be any less confident in areas like this, where there is no data to support this model. So we might try to address those problems in the upcoming sections. We'll do that by introducing the Bayesian formulation first, and later on we'll come back and look at nonlinear regression and also introducing other kinds of priors and constraints. So, the Bayesian approach to fitting our regression model. We still have the same likelihood as we did before, so probability of W given our measurement data and our model is a normal distribution using our full sensor matrix and our gradients phi. It's also got this covariance based on sigma squared times the identity matrix. Now our prior is saying that our gradients phi are zero mean and they have a spherical covariance. So zero mean means we want our gradients to be small, ideally, but we're going to be quite forgiving about that and generous initially, allowing the gradients to have a very large covariance. This sigma p squared is to distinguish it from the sigma squared that we have in the likelihood. So the p stands for the prior. The other thing to point out is that when we plug these two normals into Bayes' rule and substitute them in for our Bayesian formulation of regression, we have this prior term, prior of phi, given all our sensor data x. Now it's frequently written as just probability of phi because what this is saying is it's kind of an unsupervised model, unsupervised prior on phi. It's saying you can look at the data, at the sensor data itself, as long as you don't look at the W's. Now this Bayesian formulation, if you're wondering where it comes from, we can derive it ourselves by looking at the joint probability of phi and W given x. So let's write that out. The joint probability of our model parameters phi, that's a vector really, and W given x, so that's an x matrix and a W vector, but I won't keep them each time, can be factorized in two ways. We can focus on probability of phi given W and x, but now we have to think about the conditional probability of W given x, or we could also have factorized it as the probability of W given phi and x, and of course then we have to multiply by probability of phi given the x matrix. Since we're learning right now, that means we want to estimate our posterior over phi, so we're going to focus on that term, probability of phi given W and x, and we can just rearrange our terms so we still have the same right-hand side, probability of W given phi and x times probability of phi given x, and now you see where that phi given x comes from, and we divide through by probability of W given x as our normalizing factor. This gives us our posterior over our model parameters, but you could also see how at test time we can come back and look at our posterior over our world state. Now, when we plug in our two normals, we multiply them together and we get a new normal distribution over phi. This new normal distribution takes into account the prior on the likelihood and the prior on the model parameters. so sigma squared and sigma p squared respectively. And you might note that we're using this A matrix, which includes taking the inverse of potentially a very large matrix. We said that X is d by I dimensional, and so that's going to be d by I times I by d. So this gives you an A matrix, which is going to be on the scale of d by d. Now, if your data dimension is very big, right, that means you're going to be inverting a very large matrix, and we'll come back to that shortly. Now, let's just take a look at our model parameters again. So on the left, we have the model before we've looked at any labels, so the prior on phi, or that was our very broad zero mean Gaussian. And on the right, we have the posterior on phi. What happens to our model phi after we've looked at all of our training measurements and our training labels? And you should see that it's shifted over to the left, and it still says lots of models are possible, an infinite variety of them, but some are much higher probability than others. Now, when it comes time to inference, we're going to use all of those different versions of our models right here, and we're going to use that as a weight to make the prediction of what is the distribution of on W star, our test datum X star. So you'll see again, we had created a new normal distribution for our model, and we multiply that by our likelihood for a given W. And so we get a normal on W times a normal on phi, and we can rewrite that as a new normal distribution on either one of them, and we write it on new normal distribution on W star. It looks like a complicated equation, but you have all of these ingredients. You have the sigma squared, you have all the ingredients for the A matrix that we just discussed, and you have your training labels W. Notice now we have the posterior for W star, and we've integrated out all of our model parameters d phi. To illustrate that, we can see what our posterior probability on the model looks like. We have that from the previous slide, so some versions of phi 0, phi 1 space have higher probability than others. And then for different models, if we had just looked at version phi 1, so one sample of our model, or a different one, we would see different lines at different angles trying to explain W star as a function of X star. But because we've integrated them all together, you're averaging them all, it's a weighted average, and you get this posterior probability of W star given X star, where you should see now still a kind of slanted shape to our curve, but you see that it gets much fuzzier towards the edges away from the data. So areas like this have much lower probability because there's no data supporting them. Basically, the uncertainty in our model is helping us to say we have low confidence here, but we have high confidence in these hot areas. Now, we mentioned that A matrix was going to be quite big if D is large, and that could be a problem. So in high dimensions, you'll have real trouble inverting that A matrix. And so this is where the matrix inversion lemma comes in. Instead of dealing with inverting of something that's D by D, you can use the matrix inversion lemma to invert something that's I by I. So really the trade-off is, do you have few training examples, or do you have small dimensional data? If you have small dimensional data, just stick with the original formulation for A and invert that. If you have a small number of training examples, which happens quite often, especially when you're training from human annotated data, then you might prefer to use the matrix inversion lemma, also known as the Woodbury matrix inversion lemma. And so you can work through the formulation here, but it's just linear algebra. So far, we've done the model's mean, but we haven't done the covariance. So for fitting the variance, even though we're doing Bayesian regression, we're going to fit the variance using maximum likelihood. And in this case, that means we're going to marginalize out the gradients, which we've just estimated, and then do a maximum likelihood estimate of our sigma squared. Now we're going to build on what we've just done, but apply it for nonlinear regression. And this will be surprisingly easy if you've understood what we've done so far. We said that our model can only do linear regression, and in the Bayesian formulation, at least it knows when it's got low confidence because it's far away from the data. But to make these wonderful nonlinear curves, we have to employ a new trick. We're going to keep the math of the linear regression, but we're going to extend it with nonlinear functions. And this is the simplest way to do it. We take our old linear regression model where we have phi vectors, a phi vector applied to our measurement data x, and instead we're going to do nonlinear regression where we have a different phi vector applied to some z vector, where z is simply a nonlinear function of x. And we can come up with different functions of x, but we can start off with some nice basis functions, some ones that predefined functions that we choose. They're just going to transform x, give us some output, we store it as z, and after that we just apply the same equations we had previously for linear regression, but we do it instead for to accomplish nonlinear regression. All right, so what does it look like to choose some function of x? Well, we can have our normal on w, and it could still be some function of x. So we have xi, but we can also square x and take it to the third power, and we'll have our coefficient phi 0, phi 1, and so on. So this is a special case where z would simply equal a 1 at the beginning of every entry of zi. The xi element, so that would be the original element from our sensor data, but also the squared version and the cubed version of x. With that as our z, we can now do everything we did before when we were solving for phi, but now we're solving for the phi's that help us model a nonlinear function, a nonlinear relationship between the inputs x and the output w. When we do the maximum likelihood version of that, you'll see that it's the same set of gradients, phi hat, as we had before, except now they're expressed in terms of capital Z, as in the data after it's been transformed by our nonlinear function. So when the capital X used to be d by I, now the dimensions of Z will still be something by I, but that something will depend on how big your nonlinear function was. In this case, we had said that it was transforming every x into a 4 vector. Instead of polynomial regression, we can do radial basis regression. So radial basis function is any spherically symmetric function. Here we're using Gaussians, and so we're going to transform every input x using a Gaussian, where our alphas control the centers of the Gaussian, and the lambda is a scaling factor. Notice here that all the lambdas are the same, but we have different centers for each of our Gaussians. So if we look at our bases, which are color-coded here, you'll see that the first element, z1, is this normal distribution centered here, and so on, z4, up until z7. Now you see here there are 7 elements, right? The first one, this 1, is actually this black line here, because it's indicating that there could be some constant offset. And all the other, that's basically our prepended one that we had previously. And all of the other elements of Z are allowing our x's to be transformed using different Gaussians. Now, when we estimate phi, we're no longer weighting the different dimensions of the x data, we're weighting the different nonlinear responses of Z to x, which means that after we've done maximum likelihood training, for example, and we look at figure C here, we see that our basis functions have been scaled up or scaled down, or in the case of Z3, it's actually been scaled by a negative. The maximum likelihood version of phi has told us how much to scale each of our basis functions, so that now when we look at the total response of phi times our nonlinear version of our data x, and we transform the mean according to that function, phi times z, we get this nice nonlinear curve here, which goes through our data points, but all the time still looks like a Gaussian. If we plot just the mean of d, you'll see that in figure subplot A, where you see this nice line going through, or as close as it can, to all of the data points. Arctan is another viable nonlinear function, and so we have our z vector here made up of 7 responses to x. Each one has a different offset, alpha 1, alpha 2, but the shape of each arctan function is the same. Again, we can learn the parameters of phi in the same way as we had before. The equations don't change, just the responses to x, the function of x that transforms it into z changes. And so in the end, again, we have a nice nonlinear function that travels through the points as much as possible. Now, of course, the nonlinear response that we choose has an impact on this final model, and so you could choose a really good one, you could choose a terrible one, and partly that means also choosing your nonlinear parameters as well. So you might want to optimize those in some kind of hyperparameter search. Okay, when we resume, we'll come back and talk about kernelization and Gaussian processes.